All right, so we are going to review some of the basics. We're going to talk about phases of matter, so solid, liquids, and gases. And so your author of your book, he defines phases a certain way. So this might be different than what you guys have heard before, but how he defines it is the degree to which molecules are attracted to each other. So we've been talking about this intermolecular force, molecule to molecule attraction. So the way Rosengarten talks about it then is the phases will depend on how much these molecules are attracted. So where do you think the most attraction will happen? Where they'll be the closest? What phase? Exactly, a solid. So solid phase is where the molecules are closest together. So in terms of their IMF, we're going to circle strong. They're going to have strong molecule to molecule attraction forces. So reviewing back to our shapes, do they have the ability to change shape and volume, or is a solid firm, it's set in its ways? It's firm, it's set in its ways. So we say that it has definite shape and volume. Neither of those can change for a solid. Now, when we start to have some movement to flow, yet there's still attraction between molecules, is with liquid. So we have our liquid phase. So free to flow, but there's still attraction. So thinking about what it means to be viscous or viscosity, what do you think that means per attraction? So thinking about relative strength, what would have higher IMF, water or honey? Honey, why? It's thicker because of what? The stronger attractions, right? So the way I want you to think about it is higher IMF, you're going to have stronger viscosity, or it will move slower. Well, yeah, it's the movement if you were to like pour it out of something. So in our case, our liquids, we're going to rate them as moderate strength of attraction forces. So strong, they really want to be next to each other. Liquid, they still want to, but they can flow a little bit.
So does honey have stronger bonds than water?
Not necessarily bonds. We're not talking about bonds. We're talking about molecule to molecule attraction. So
it's the attraction then for honey is the attraction.
Not necessarily. What type of attraction forces there are? So we talked about dipole, hydrogen bonding. So I don't know exactly off the top of my head if honey can hydrogen bond or not. I don't think so. Maybe parts of it. So water is stronger in the sense that it can make this really clean hydrogen bonding versus like honey might just have some dipole interactions. So, good questions. I like it. I feel like this unit's been getting getting your guys' brains moving a little bit. All right, so liquids, what do we know is for sure cannot change? Shape or volume cannot change for a liquid. Volume. All right, so we have definite volume, but it can change shape. So even though I pour, maybe I fill this halfway with coffee, it's not just going to magically fill up because my cup's bigger, but it will change the shape depending on which way I turn it. Then if we have gas, we think of this as no issues moving past each other. So there's little to no attraction between the molecules. So they have weak IMF. And then if I were to put gas into a container, it would take its shape and its volume. So it has indefinite shape and volume. As a little bit of a review for our phases. So I drew in some diagrams here of my solid, liquid, and gas phases. You don't need to draw them exactly, but what are the major things that your solid box should have? How should the atoms or the molecules be arranged? Tight, neat, uniform. Liquid, I give it a little bit more space because they start to be able to move freely. But gas is when they really have no issue moving past each other. All right. So the way I want you to think of this is strong IMF on this side, weak IMF. All right. Now, we're going to start talking about how energy comes into play here. What do you have to do to make an ice cube melt, go from solid to liquid, right? You add heat. What do you have to do if you want to make some ramen noodles? What do you have to do with your water? You got to boil it, right? You got to add heat. So moving in this direction, I want you guys to think of heat as energy. So you're really adding energy to your system. And so we're going to review these terms here that discuss if it's endo or exothermic and what it means. And so these are just in terms of, is energy going in your system or away from your system? All right. So well, how I want you to think is endo. N is like enter. And X is like exit. Okay. So in endothermic processes, you are adding energy. So energy is entering. So add energy to your system. Where exothermic would be release of energy. And oftentimes we see this as heat. So our exothermic reactions get hot from the system to its surroundings. All right. So these are just some terms that we're going to have to use as we kind of work our way into heat curves. All right. And so another thing just to review, you guys will have to know these terms, but they're the terms associated with different phase changes. All right. And so we're also going to talk about which direction are we adding or removing heat. Who can tell me what we call it when we go from solid to liquid? Melting, melt. So the proper term for solid to liquid is melting. What about liquid to gas? Or boiling. So you're going to hear boiling or vaporizing. These are going to be your terms that I will use. What about if we go from liquid to solid? Yep, freezing. What about gas to liquid? Wonderful, condensation. So when you guys are drinking a nice cup of lemonade on a hot day, all right, on the side of your glass, you get some condensation. Who can tell me what it is when you go solid to gas? Or yeah. Yep, exactly. Sublimation.
Didn't even ask the question.
What about gas to solid? Of course, deposition.
Oh, that's right. Okay, come on. So
Now thinking about this, which direction, going solid, liquid, gas, or gas, liquid, solid, are we adding though that heat? Yeah, right? When we go to solid to gas, we're adding heat. So what is that term we say goes with add heat? Endothermic. That means if we go from the direction of gas to solid, that's going to be our exothermic processes, where we're releasing energy back into the surroundings. All right. Any questions on these? All right. So now we're going to get into heat curves. You guys are going to have to be able to know how to draw these, read these, answer questions about them. And so these are ways that we can visualize the phase changes going on. Now, this graph has a bunch of terms for you already labeled, but that's not going to be the case. A lot of times you're going to have to identify where the solid, liquid, gas is, where the melting, boiling points are, etc. Okay, so we're going to start basic with a lot of these things built in for you guys, okay? So how to read these is that we have to think of it as line segments. So this would be line segment A to B. That's where our solid exists. So notice this is at our lowest temperature, okay? Then we are hitting a plateau where solid and liquid exist, all right? So thinking about it, at our melting point, this is really a combination of our melting and freezing, all right? If we start to melt, we're gonna see some of our liquid and our solid. This happens at a specific temperature depending on what we're dealing with. Then as we move on to the next line segment between C and D, this is just liquid. Then our boiling, we're gonna have a combination of liquid and gas existing here. And lastly, at our highest temperature, that's where just gas exists, okay? So you guys are gonna have to be able to identify, because it's not always gonna be an endothermic heat curve. How do I know this is endothermic or heat's being added? The temperature is going up, that's exactly right. So what I want you guys to think about is energy and temperature being related. In this case, specifically kinetic energy. So temperature is a measure of kinetic energy. So if we're seeing our temperature go up over time, we must be adding heat in our system. Therefore, this is an endothermic heat curve. So I'm going to write up here that this one is endothermic. And I'm going to write temp increases over time. Now, notice how our phase changes are happening and the temperature is staying constant. All right, so this is kind of that first question that's below this. Why are there plateaus or flat parts? So we know it's where our phase changes are happening, but why do you think it's a plateau? The temp's not changing. What does that mean about our energy? So it's not what type of energy? What did I just say to associate with temp? It's not kinetic. So what other energy must it be? Potential, exactly. So phase changes are a change of potential energy, not kinetic energy. So really the energy that we are adding into our system starts to go into changing that potential of the molecule. So if you guys were to be boiling your pot of water, if you were to stick a thermometer and from the second it starts boiling to 10 minutes into it, the temperature will read exactly the same. So I just want to make you aware that there are terms associated with the two plateaus. And so I'm going to move this a little bit. You guys can find a spot to fit it in. Maybe I'll just pull it over here. So we're going to have what are called heat of fusions. And so this is an energy term associated with melting or freezing. It doesn't matter which way you go. And so this is going to have units of joules per grams. So we have to remember that our joule is a unit of energy and gram is a unit of mass. So really what these values tell us is how much energy it takes to melt or freeze a gram of our substance. Okay, so that's how I want you guys to think about this. Then for the boiling or condensing, this is our heat or delta H of vaporization, and it's usually abbreviated as HVAP. This also has units of energy per mass. And so again, these are terms associated with these phase changes saying, hey, does this substance take a little bit of energy for it to happen or a lot? So just comparing the melting and boiling plateaus, what do you think takes more energy to melt water or boil it? You're correct. It's a longer plateau. It takes more time. And so typically we can associate a longer time with more energy because I want you to think of this whole graph. The energy being input is constant. It's at a constant rate. Okay. Now, I have a question for you. I know this is water. How could I tell? What off this graph would tell me that it's water? The melting or boiling point. We know what those should be for water. So water boils at 373 Kelvin, and its melting point is at 273 Kelvin, or as you guys also know, 0 degrees Celsius or 100 degrees Celsius. This is just a different scale. So I can say, yep, that melting and boiling point matches. This has to be water. Kelvin is even more science. So like Celsius is like what the rest of the world use. Science likes to use Kelvin. The relationship is Kelvin is equal to degrees Celsius plus 273. All it is a shift of the scale. It's not as funny as it is to go between Celsius and Fahrenheit. You just add 273 to anything in Celsius to get Kelvin. Yeah. You have two phases that exist simultaneously. And so those happen at our plateaus or phase changes. So I want you guys to think about this as an equilibrium, because if I were to have an ice cube and I put it at 0 degrees Celsius and I hold that temperature constant, really what's happening is the freezing and melting phase changes are happening simultaneously. Notice how this graph doesn't give you anything besides the line. So this is exactly what I want you guys to be able to identify where your phases are, where the melting and boiling points are. And then we're going to take it even one step further and be able to give amounts of time to each of these phases. Friction is a thing. They're claiming friction's not real. Anywho, okay, so who can tell me where the solid phase is between what 2 points? What line segment? Solid. A and B. How do we know this? It's the lowest temperature. So this is a great conversation because it's not always where it starts. This is an endothermic reaction. Exactly. This is what an exothermic reaction looks like. No, you don't have to. No, you can if you want. But what I'm just explaining is this isn't the solid, right? Even though this is where it starts. What phase would this be? Gas, right? It's at our highest temperature. So how I want you guys to look at these is that as temperature goes up, which we're seeing, you're always going to have your solid at the lowest temp, okay? No matter what side of the graph it's on. So I'm going to right away identify that this is my solid. Let's see. I'm sorry. Oh, that's because Bob didn't open it all the way and I haven't touched it. All right, so what phases then exist at our first plateau? Solid and liquid. We have to include both. Because what change is happening? What type of phase change is here? Exactly, this is our melting between B and C. Then C and D is just what phase? Liquid. Then we move on to the combination between D and E, our next plateau, liquid and gas. And then finally, at our highest temperature, we end with our gas phase, okay? So don't forget that the second plateau then is our boiling. Okay, so these are some of the questions that I would ask. So how many minutes pass from the first appearance of the liquid phase until the substance is entirely in the gas phase? So the idea is figuring out between what 2 points. All right. So when do we first see liquid pop up? Exactly. At point B is our first site at 4 minutes. If I were to drop down and look, B happens at 4 minutes, right? Oh, someone want to let them in?
Whoa.
Okay. The next thing that we see or is when it's entirely in the gas phase. At what point does that happen? E, 34. That's the beginning of when all the liquid has finally been turned to gas. So we're going from B to E, which is at, if we look, 34 minutes. Okay. So how much time was it first appearance till it's gone? 30. Exactly. It's the difference. So the next question says, how many minutes will it take your water to undergo melting? So we are just looking at what plateau, our first one or our second one? First, right? We're just looking at the line segment BC, which B is at 4 minutes. We have 8 minutes for C. So you're just looking at the difference between the two. It takes 4 minutes for us to melt water then. All right. Is how many minutes is the water completely made of a crystal lattice? What do you think I mean by made of crystal lattice? Exactly. So this is how many times is it completely in the solid phase? 4 minutes, exactly. The only time it's only solid is between A and B, which gives us 4 minutes. All right. What segment is when water is in both liquid and gas? What did we label off of our graph? Exactly, the boiling point or segment DE. All right. And then how many minutes will it take to boil once the temperature is reached? This is just now asking how long did it take to do the distance between D and E? I think I heard it. 14 minutes, exactly. E is at 34. D is at 20 minutes. The difference is 14 minutes.